So you've done an R&R study and you get a low result, that is a high percentage, a too high percentage. Now what? What do the numbers tell you? Stay tuned. Hello, I'm Tom. Welcome to my channel where we talk about continuous improvement in an industrial setting. And today let's dive in a bit further on when you do a Gauge R&R study, so that's a reproducibility and repeatability study, and you get a too high percentage, so that is a low score, a bad result. What do those numbers tell you so that you can actually make improvements? So what to focus on? Because indeed the R and the R, but also a couple of other things in the whole study, in the scoring, will tell you which areas you most likely have to focus on. Now first, let's go over this, what is high and low and good and world-class in R&R, just to get that base set in again, and then I'll explain how it is built up and how we can see where to first look. The idea is that every system that you have, so every process, it has a distribution. We have again our nice normal distribution curve, and that we have, and this is already basically your part-to-part variation. But you have an observed or a part-to-part variation. Those are a bit difficult to split apart, and this is just the variance that is in your system. So when you try to make the same part every time, you still have a distribution in. If it's a bit bigger, a bit smaller, and most of them will be dead on the center line. At least that's what we hope. The idea of a Gauge R&R is to check not if your process and your product are within specs. It is specifically to check whether your measuring system, so your machine that measures, your measuring tools, your laboratory, things like that, whether they operate correctly, whether they are accurate and precise enough to do the measurement that you need to check whether your products are within specs or whether your products are differing one from another. Now, so that here, the idea is that when you have this normal variation from your process, there is always a little bit of noise coming from your measuring equipment. And I'll put it in a bit with red, and then afterwards show you how much the noise should be for one part. But let's say everything has just a little bit. So all the values are just a little bit skewed. And if everything has a little bit, then what you basically see is that instead of the real part-to-part variation, your observed variation will be slightly bigger due to also some variation coming from the measurement. So you're actually seeing a bit more variation. Now, this way is pretty difficult to judge. What does the Gauge R&R do? It sort of eliminates the whole green part, and it sort of tries to back calculate only if you would have exactly the same part, what your measurement system would be doing. And you hope that that is a very small distribution. In fact, what you want is that this distribution is less than 10% of the green one and also less than 10% of your spec range. And there's a bit of debate whether you should use the observed part-to-part variation for this testing or you should use the spec. I would actually say use both of them, but you sort of use the smaller one usually. In the end, if you have a set spec range, you anyway want a tenth of that, but also if you have a product range, you need to find it over there. Anyway, those are the details more for the how to do an R&R video. This is the ideal system that you see. So that part. The idea is that this measurement error divided by your range you see, so the observed part-to-part variation is less than 10%, then it is good. Now, if it is more than 10%, and specifically in sort of your rule of thumb, if it is more than 30%, then you really have a problem. Then it's not a correct measurement system for your application. Between 10 and 30, it's usually good enough, but you'll have to see a bit what are you doing with this measurement system. Are you just doing some fail and pass type of measurements? Do you just want to get a broad insight and just know where your product is going? Then it's all fine. Do you really want to use it to upgrade performance or to make changes in your system? That is, are you doing the type of Six Sigma work where you are looking at parameters, changing them a bit, then looking at the result in the product, and based on that you want to decide which parameters are best? Then you really need to get a measurement system that is a lot less, or at least less than 10% of your spec or observed range. Now, we've been talking about the variation that you observe, and there are basically three variations that you really need to pay attention to. The first one is that part-to-part variation. That is our baseline, so that is not part of the measuring system. The other two are the R and the R. So repeatability and reproducibility, they are the machine variance or equipment variance and the operator variance. We are calculating, and remember here that we make usually something like 3 to 5 different operators and do trials on, let's say 5 to 10, 10 would be good, different parts, and they test each of those parts also, 3 times, maybe 5, but roughly 3 operators, 3 times 10 parts. That's a basis. That's sort of the minimum that you want when you're doing an R&R. And that means that we can then calculate, using statistics, the difference. See, each part is then measured, and we take the 3 by 3 by 10 here. It's measured 9 times. So one operator will be measuring 30 times. 10 parts, 3 trials. What we can do then, and that means that in the end, we have a whole load of measurements. Every part, because it is measured 9 times, we can take a nice average, and all of those measurements will make sure that we get a pretty accurate measurement of this part. I mean, if different operators tried it a couple of times and you average all of that out, well, then you're pretty close. So comparing all of those averages to each other, we can see what is the variation, and this is basically already normalized into these averages, so the variation that's really in the parts. In the same way, we also see if you repeat each measurement, so each part measurement 3 times, but you have 10 parts also, you can see that one part, it gets measured 3 times by the same operator, but the difference must be more in the equipment. Now, of course, it can be that an operator just very poorly reads the equipment, cannot work with the equipment. But what we basically say is that when those 3 repeats, they show a lot of variation, then we call it equipment variance. It is not a repeatable system. So the result cannot easily be repeated on the same equipment by the same operator. And this one, I mean, 3 measurements, that might sound not so many, but actually we're doing that 30 times, because each operator has 10 times that you do these 3, but also we have 3 operators, so we're checking that whole bunch of 30 times a comparison of 3 values that measure the same thing, and we all put it into the equipment variation. Now the operator variation, that is where we take the averages of everything that one operator does. So we don't have a lot of degrees of freedom in this statistically. What that means is we have a lot of data points within one operator. So one operator does 10 parts 3 times, so that's 30 measurements, but we average it all out into one average per operator, and then we check the difference between the operators. Now we do take the ranges also into account, but basically you only check, you have this whole set, it should be the same, And do we see that there is a difference between what the operators find? So is there maybe one operator that has a much higher score for the same parts in the end than the other two operators? Then we have a difference in the operator. Now that immediately gets us into the directions where to look. So first off, and this is not even really the measurement system, but I think it is an important one to hit right off the bat. That is when the part-to-part variation is larger than your specification range, and this has nothing to do with the measurement system, but when the green line is a lot wider than your specification range, you have a problem with your process itself. So you need to improve the process to get your process capability, your CPK up, and you might need indeed to have a better measurement system to do this, but the problem is not per se in the measurement, it's really in the process itself. So that's when the part-to-part is a lot higher. The other two, they come in, and the name sort of suggests it already, when we see that there is a lot of difference between 3 repeat measurements of the same part, then we have a very difficult to repeat measurement, and probably it will be in the equipment or maybe the training with the equipment, but then it's if all the operators also have that same spread. And what do we mean here with equipment? It's not even per se that the equipment itself is off, and that means is giving wrong values. It means that it is hard to get a good reading from the equipment. So it can either really change the number for each measurement, and you can really easily read the machine. It can also mean that it is just difficult to get a good reading, so to interpret what it's saying. If we, for instance, take measuring the thickness of a bit of wood, and we take calipers, so these very precise range meters, right? The millimeter or inch measurers, they have this, the caliper has this clamp thingy, and the clamp is easy because you can put it around and it gives you a very good basis, and then you read how wide it is. Now, if we were to do a similar thing with a normal ruler or just some measuring tape, you have to put the measuring tape on it and look, okay, this seems to be that mark on the tape. Now, seems to be that mark on the tape is a lot harder to get exactly the same every time. And this is why those calipers, they are very good for measuring things where the tolerance of your measurement error is very low. And this system is just easier to read. Now, then, well, easy to read, there we actually have the other thing with these calipers, and that is if you have the traditional ones, where you basically read the millimeters on the main scale, and then on a secondary scale you can read those tenths of millimeters by checking which of the lines actually really match, and then the next one doesn't completely match. That system, you need to know what you're doing. I mean, for engineers, this is one of the things that we are sort of proud of, that we know, but we learned it in school, in wherever we learned it. This is not a natural way of reading exactly what your tenth or hundredth of a millimeter is. What you also have is digital, and there you just have a display that reads it out to you. Now, a display is a much easier way for the operator of the equipment to read what the indicated value is. It can still be that the electronic measurement is not correct, but at least reading it is a lot easier. The operator, on the other hand, that is when you do see that the range between the trials within a single operator's trials is pretty small, but between the operators you also have big differences. And here we go to training, and again, how to read the scale. Because if the equipment shows the variation, it can be that the scale is difficult and it's just, one operator sees different things every time. But it's also a big chance that it was the actual measurement that is just difficult to do. And especially if you have all kinds of indirect measurements, big chance for that. Microbiology is very infamous for having this problem in if you plate exactly the same sample a couple of times over different plates, you get different results of colony count, things like that. Now the operator, that means that either you have not trained your operators correctly, and especially so if you think that it might be mostly an operator thing within your organization, make sure that you get not 3 but 5 or 6 operators to do the R&R study. And if you see that 2 or 3 out of your 5, they have really nice, very tight equipment variances, so very small equipment variances, and the others do not, then check, are these the people that are better trained or more experienced? Then you have a training gap. When you see that the equipment difference is not so big, but there is still quite a large difference in the averages between your operators, probably everyone has their own way of interpreting how to read the device or exactly how to look. And there are many measurement systems where, like the calipers, if you always just pick the millimeter and someone else always picks the next millimeter and someone else always picks with the secondary scale, you have 3 different ways of using the same tool that will produce different results. And if we go into more chemical and microbiological analyses, you will see this a lot. People just looking from the left or looking from the right or the top or bottom of a fluid pipe, that will give you a lot of different standardized ways. So for each operator, for themselves, it is standardized. They have a pretty good repeatability with their own measurement. But when you ask somebody else to do the same analysis and just go for the same parts, you find that it is not a reproducible result. Now the other thing here can of course be, but then it's a different day or environmental circumstances. So do take this into account. The operator difference can have some difference from, even if you use it to bring it to different labs, it's not just the person, but also the person and the lab. But if you do it on different days or with different batches, things like that, it's not ideal, but sometimes you have to do it like that. Weather or maybe a wrong calibration before you start doing the measurements, so such type of environmental factors can really affect it. Although if you do a nice and tight R&R study where you do one calibration for everyone and also just try and do it with the same batch in the same circumstances, then we're really looking at training and explanation of how exactly to prep the sample and how to measure and how to interpret the measurement. When we have equipment variance, then we are really looking at the machine probably has difficulty repeating the same result, so getting exactly the same value because it has slight changes every time, and or we have indeed a difficulty in reading even when you try to read it in the same time, in the same way every time, it's difficult to read. And then the part-to-part, as I said, these two we add up, divide by the part-to-part. If the part-to-part itself is very high, you will get a nice R&R, by the way, because if the divider is very big, then we get a small number, small percentage. But if it's bigger than your specifications, you have a problem in the process, not in the measurement system itself. So when you see high equipment variation, it's either the machine or the way to read the result. When you see high operator variation, also check how difficult it is to read correct results, and probably you have to work on the skills of the operator, so training and just making the system easier to use. Now I hope that explains a bit what direction you are going to look at when you see a too high percentage, so that is a bad R&R result, because in the end we don't do a measurement systems analysis because we want to show a percentage and just say everything's fine. We do it to find ways to improve, and we need to know what directions to first look at when we improve, that'll make our improvement a lot faster. Now, I hope you enjoyed that video. If you did, don't forget to hit that like button, and also drop me a comment which part of measurement systems analysis or any other Lean or Six Sigma topic would you like me to address. And is this new info, or do they still teach it nowadays in colleges? I would love to know that as well. For now, I wish you the best of luck in your measurement systems analysis, and don't forget to enjoy the improvement journey.